Close your eyes for just a moment. Picture yourself standing at the absolute edge of Europe. The wind is constant, cold, and completely relentless. Ahead of you, a stretch of dark, churning ocean that has stopped entire civilizations in their tracks for thousands of years. That body of water is the Strait of Gibraltar. And somewhere beyond that haze, just 14 kilometers away, is the continent of Africa. Close enough to see on a clear day, but separated by some of the most violent, unpredictable, and unforgiving water on the entire planet.
Engineers have been studying this crossing for decades, and every single time, the math led them to the same brutal conclusion. The currents here do not simply flow, they war with each other. The Atlantic Ocean crashes directly into the Mediterranean, creating underwater turbulence that no instrument can fully predict or measure. And the depth. In certain zones, the seabed drops nearly 900 meters straight down. That is deeper than 3 Eiffel Towers stacked directly on top of each other. No conventional bridge foundation could survive that. Not difficult. Not expensive. Flat out impossible.
But then, one team of engineers stopped asking the old question. They stopped asking how to build a foundation that reaches the bottom. And they started asking something completely different. What if the bridge never needed to touch the bottom at all? What if instead of fighting the ocean floor, you simply ignored it? What if you could suspend a 100,000-ton highway in open air, floating, tethered, but never grounded? That single shift in thinking changed everything. This is the $80 billion intercontinental bridge between Spain and Morocco. And this is how you build the impossible. Every megastructure begins with its foundation, and this one begins not in the ocean, but on dry land. Massive industrial facilities are established along the Spanish coastline. Inside, thousands of workers assemble colossal steel skeletons, frame by frame, weld by weld. Every joint engineered to withstand forces most structures never encounter. Once the steel framework is locked in, the concrete pour begins. And this is not a normal pour. It runs for 72 hours straight, no breaks, no pauses, no stopping. Because a single interruption creates a structural weakness that simply cannot be undone. What emerges from that process is genuinely staggering. A hollow, reinforced concrete structure, almost 700 feet long, weighing 73,000 tons. Essentially, a skyscraper laid on its side.
Now here is where things get strange. To move something that weighs 73,000 tons, you make it float. The dry dock is flooded with water, and slowly, almost gently, this enormous concrete structure lifts off the ground for the very first time. Tugboats guide it out into the open water of the strait, into the wind, into the currents, into the chaos. but leaving it on the surface would be catastrophic. Ships would collide with it, storms would batter it, tides would shift it out of position. So instead, it is carefully submerged 30 meters below the surface, out of reach, out of sight. Suspended in place, held there by something that must survive the most extreme underwater forces imaginable: the anchor system.
This is the part that does not make it into most engineering textbooks, because securing a 73,000-ton structure to an ocean floor requires human beings to descend somewhere almost no human has ever gone. Saturation divers. Specialists who live under pressure for weeks at a time, descending into freezing water, near total darkness and almost zero visibility. They navigate entirely by feel. They plant explosives into solid basalt rock just to create a flat surface for the anchor points. Then hydraulic drills carve bolt holes deep into the Earth's crust itself. Steel anchor piles, each one enormous, are driven into bedrock. Braided tether cables, engineered to handle tension forces most materials cannot survive, lock everything into position. The ocean fights back constantly. Currents tug, pressure builds, but the foundation holds. With the underwater foundation secured, the bridge begins its rise into the sky. The towers. These are not small structures. They climb 500 meters upward, straight into the full force of Atlantic crosswinds. Engineers use a system called self-climbing formwork. It pours concrete, waits for it to cure, then mechanically lifts itself higher to repeat the entire process again, day and night, week after week, without stopping. But at 500 meters, the wind is a completely different animal. Gusts reach speeds that can destabilize both workers and structural components simultaneously. The solution is counterintuitive. The towers are not designed to be rigid. They are designed to flex. Inside each tower, a honeycomb lattice of steel allows the structure to bend slightly under load, absorbing energy rather than resisting it to breaking point. A tree survives a storm not by being immovable, but by moving with it. Now comes the most visually dramatic phase of the entire project: the main cables. These cables weigh over 24,000 tons each. You cannot manufacture them on the ground and lift them into position. The physics simply do not allow it. So instead, you build them in mid-air. A system called a spinning wheel travels back and forth between the two towers on a cable car track. With each pass, it lays another steel wire strand across the open gap above the ocean below. Thousands of passes, thousands of individual strands, slowly accumulating into a cable larger than most industrial pipes. Workers suspended at altitude manually guide each wire into precise alignment. One strand out of position compromises the entire cable's integrity. After months of continuous operation, the cables are complete, each one a masterpiece of accumulated precision. But the cables introduce a new problem that must be solved before construction can continue: wind-induced vibration. At that altitude, in those conditions, the cables begin to oscillate, not slightly, dramatically. And if left unchecked, that vibration works its way into the steel at a microscopic level, weakening it gradually until failure becomes inevitable. The solution is a series of hydraulic dampers, large-scale shock absorbers installed at regular intervals along every single cable. Each damper absorbs the oscillation energy before it can build into a resonance wave. The cable goes from vibrating like a guitar string to holding steady like a solid steel bar. It is not glamorous work, but without it, the entire structure is compromised from the inside out. With stable cables locked in place, the road deck installation begins. Individual steel deck sections, each one weighing around 100 tons, are transported across the strait by barge. They are hoisted into position using strand jacks, hydraulic lifting systems capable of raising enormous loads with millimeter-level precision. But the deck cannot be built from one side only. Adding weight on a single side would throw the entire cable geometry permanently out of balance. So construction happens symmetrically from both towers simultaneously. Both arms extending outward toward the center, perfectly balanced like a scale that must never be allowed to tip. Week by week, the two arms grow longer, reaching toward each other slowly over open ocean. And then comes the moment every single engineer on this project has been working toward for years. The closing segment. The final piece, the 30-meter steel section that, when lowered into position, makes this bridge a single continuous structure from one continent to the other. But steel expands in heat and contracts in cold. A section that fits perfectly at 15 degrees Celsius may be too long at 30, too short at 5. So the engineering team waits. They monitor temperature, wind speed, and structural movement in real time, holding until the exact thermal conditions align perfectly. When that moment finally arrives, the segment is lowered. The connection flanges meet. The alignment is perfect. And the final bolt, what the crew calls the golden bolt, is driven home. In that single moment, Europe and Africa are connected by land for the first time in recorded human history. From that moment, the finishing phase moves quickly. Road surface is laid across the full span. Wind barriers are installed on both sides of the deck. Electrical systems are activated, illuminating 14 kilometers of suspended highway above the open ocean. And just like that, what was once a long, unpredictable, dangerous ferry crossing becomes a drive. A straight, uninterrupted drive from southern Spain to northern Morocco, across the Strait of Gibraltar, across one of the most hostile stretches of ocean on Earth.
They said the currents were too strong. They said the depth made it impossible. They said no material could survive the conditions. But here it stands, and it proves something that every impossible project ultimately proves: that the limits of engineering are not fixed. They are simply the last place human ambition has not yet reached. If you want to see what else gets built at the edge of impossible, stay right here. There is always further to build.